motion. So we kind of have decided in the past that the reason things are in a motion is due to some sort of force acting upon an object. And we've talked about before what motion is when something's changing over time. And we've talked about what displacement is. It's the position, the distance over a scalar or a vector quantity. So displacement is the final position minus the initial position, and distance is just how far it went during the whole trip or the path that it took. And remember, velocity is speed. Also, velocity is vector, speed is scalar. This one has direction, and acceleration is the change in velocity. And time is when it happened. When did this motion occur? How long did it take? When we're trying to visualize motion, we use a coordinate system. We've been looking at motion graphs, and we've been defining kind of the positive direction and the negative direction. And we've been able to tell if something's increasing in velocity, at rest, decreasing in velocity, accelerating, decelerating, all these different motions depending on what the graph looks like. So if we look at position, it's where this object's happening, the distance, the displacement, and we have a little formula. So the total distance or how far it went in meters is usually x. X is our distance or displacement. And the F means final. And the I means initial, or the end subtracted from the beginning. The ending place and the starting place. It's a way to remember it. So in physics, we write it like this, x equal. The change in x is the same thing as writing the final minus the initial. So this is an important formula to remember, and we're going to use it a lot more in combination with other formulas. So again, just a reminder, we've talked about this a lot. So distance is scalar, meaning it's just a number with no real direction to it. Vector is a quantity with some kind of direction. And usually we'll represent a vector with a little arrow sign. So that would be velocity, that would be speed with no arrow on it. So again, time is just when it happened. That's easy, in seconds usually. So now we're going to get to some more complicated equations. So velocity tells us how fast an object's going relative to a fixed point. So if I'm standing here and I'm timing a car, it's moving 55 miles an hour relative to my viewpoint. And so the way we can figure that out is that change in x, which is the final spot it ended up in and the starting spot it ended up in, divided by the change in time. What time did it start and what time did it end? So usually in physics, time initial is 0 because it's when I start timing it. So that sometimes that makes our problems a little easier. So this equation is also really important, but if you don't understand what this triangle stuff means, then this equation is important to know. It's the final minus the initial value, both for distance or displacement, depending what the problem is asking, and the time, the starting time and the ending time. So it's end time minus time at start time. Okay. So when we look at how velocity changes, we call that acceleration. So if velocity is constant, there is no acceleration. But if we're going fast, then slow, then slow, then fast, and we're changing our velocity, that's what acceleration is. How fast are you speeding up? How much are you slowing down? So that's a big deal. So look at the previous equation. It's a change in distance over time, and acceleration is a change in velocity over time. Very similar, so don't get confused. And it's the same thing. The final velocity subtracted by the initial velocity divided by the final time subtracted by the initial time. And that gives us these equations. So when we're looking at these problems, we have some steps to do. So make sure you have this little list handy so you know what to do. We're going to read the problem twice. We're going to draw a little diagram of it. We're going to label our drawing. We're going to write down what we know and what we don't know. We're going to pick an equation to use, and we're going to solve it with the algebra symbols first and then put the numbers in. Those are the steps every single time we do physics. So print this, write it out, keep it by your desk so you have it always. That's always going to be what we do. I'm taking a college physics class, and that's still always what we do. So let's look at this. A girl rides her bike for 2 hours, and I like to underline things just to keep track of my numbers. So a girl rides her bike for 2 hours, and she travels 22 miles to the north of her house. What was her velocity during this trip? So let's look at this problem. So we've got a girl. Oops, I didn't want to do that. She's riding her bike. I don't have to draw a bike. I can just put a dot if I want. But if you like drawing, go for it. So here's a bike, a really bad bike. Here's the girl riding it. And she rides her bike to her house, her yellow house. And we know she went 22 miles. So that's our velocity, or sorry, our distance. Silly Miceli. And we know it took her 2 hours. So that's our time. Okay, so according to our steps, we did what we know. We labeled our drawing, and we want to know the velocity. So what's the velocity? The next step tells us to decide which equation to use. So let's look at our variables. I have x and I have t, and I need to know v. So this is the equation I'm going to want to use. So I'm going to write my equation. V equals x over t. And you might be asking, why aren't we doing final and initial? Well, initially we started at point 0, and we ended up at 22. Or we could say we started 22 miles away from our house and ended up at our house. So our final position was 22 miles from our starting position, which was 0, where we started measuring. And our time, our final time, could be 2 hours, and when we started it was time 0. So 2 hours minus 0 hours is 2 hours. So we have miles on top, 22 miles on top, 2 hours on the bottom. So now we do 22 divided by 2, and that is 11. And we keep our units because nothing canceled out. 11 miles per hour. So is that a velocity? Yes. So that's our answer. 11 miles per hour. That makes sense. That's about right. Okay, let's look at the next one. A boy rides his bicycle for 2 hours and travels 11 miles to the north of his house, and then travels 11 miles back to his house. What was the velocity during his trip? Okay, so we've got this boy. He's on his bike. His bike looks worse because my computer did something weird. Okay, so he rides his bicycle for 2 hours and travels 11 miles to the north of his house and then back. So he's actually starting at his house. And then he travels 11 miles. That's a distance. But then he travels back to his house another 11 miles. So that's going back the other way. So if we're doing displacement, He's going 11 miles in the positive direction, and then he's going 11 miles in the negative direction. If this is our house, we went 11 miles this way on our motion map, but then we went 11 miles this way on our motion map, so he's coming back the other way. It also took him 2 hours. What was his velocity during this trip? So our v still equals the change in the distance over the change in the time, which is the final distance minus the initial distance, or the final position minus the initial position. You can use x or d here, it's the same thing, over the final time minus the initial time. Whoops, let's write it the right way. Sorry, I did it wrong. I didn't write it the physics way. Hold on. Pointer, eraser. I just want to erase this part right here and fix it. So it's going to be time final minus time initial, or time final minus time initial. Okay, so when I started and when I stopped. So my final position is at negative 11 miles minus my initial position, which was a positive 11 miles, divided by my time. Well, my final time, I started at time 0 and I went out and back, and the whole thing took 2 hours. So now I have a bunch of negatives here, but that's okay. So if I do negative 11 plus negative 11, that's negative 22 miles. 0 minus 2 is negative 2 hours. I put that in my calculator. A negative divided by a negative is a positive, and it means I was going at 11 miles per hour. So don't get freaked out if the negative sign is there, because it's indicating a direction, but the math will make it all work out. So always remember this one as a good example for you. Okay, so these equations are something you just need to have. You don't have to memorize them, but you have to know how to use them. And just by using them, you'll start memorizing them. So you can print these out, you can write them down wherever. I'll put them on the test for you. But just because they are there does not mean you know how to use them. You have to practice using them so you know what to do with them. So this is a kinematic equation. If we know 3 of these variables, we can solve for the 4th one. So this is our final velocity. This is our initial velocity. A is acceleration, and t is time. So if we know 3 of those things, we can solve for the 4th thing. So that's one equation. This one's a little more intimidating, but not really. We know all these letters. Let's look. So this one is saying the final position, or the final distance, is equal to the initial position, which a lot of times is 0, plus 1/2 times the change in velocity. Remember, this is a change in velocity. So final velocity minus, or plus, this is weird, plus the initial velocity. So whoops, it is not the change. So it's final velocity plus initial velocity times however much time it took for all the whole thing to happen. So again, if we have 3 or 4, there's 1, 2, 3, 4, there's 5 variables, so we need 4 of them to be able to solve for this one. A lot of times, our initial velocity is 0 because it starts from rest. So if it's 0, that means it was at rest, and we don't have to look for that number or that variable because it's 0. It's not moving. Okay, another valuable one is our final position is equal to our initial position plus our initial velocity times time plus 1/2 of the acceleration times time squared. This one's confusing, but it helps us to find time. A lot of the problems we get, we need to solve for t. And the nice part is a lot of times the initial velocity is 0, so you can just ignore this whole part of the equation if that's true. And then it's just 1/2 at squared, which isn't so bad. Get the calculator. Okay, another one is if we have to solve for velocity, but we don't have time. See, there's no t here. So we have our final velocity, but it's squared, is equal to our initial velocity squared. I spelled initial wrong. Initial velocity plus 2 times acceleration times the difference, the change between our x's, our distance, our final distance subtracted by our initial distance. And then always remember, we want to always solve for v final, so we have to take the square root of all that stuff. Your calculator will do that for you. And we'll practice doing it. So these are all the equations. So I literally have them right next to my screen right here off camera, so I can look at them all the time. And that might be a good thing for you to do also. Write them down. And then we're going to work on solving. What if we need to solve for A and we have all the other things? We have to know how to rearrange these equations. So we need to know how to put A equals VF minus BI divided by T. We need to know how to arrange these to solve for the ones that we're going to need. So we'll look at that at another video. Okay, I think that covers it for today.